We have previously talked about derivatives at a point. In other words, the slope of a tangent line at a particular point. And we have a few ways of doing that. And and they involve limits. So just to remind ourselves, so say we're looking for the the derivative at this particular point. This point meaning the point when x is negative 1.2. This is just an example. I'm not specifying that this works for all functions or all functions look like this. We're looking at the rate of change at that particular point. We're talking about the slope of the tangent line, and we know that we get that slope. We find the slope of a tangent line by finding the limit of a secant line as the 2 points of the secant line get closer and closer together. So what we get is we get a specific number. Right? We calculate the limit of the slope of secants, and we find the slope of the tangent line. And of course, that's going to be a number. In this case, it looks like it would be a negative number. The slope of this tangent line, this purple line here, is a negative number. But this depends, the result depends on where in the function it is. Let's say we have another point. We want to find the slope of the tangent line at another point. Well, it would be another number. This would be a positive number. I'm not sure exactly what it is, but it'd be a positive number. So the slope of the tangent line depends on what value of x we're talking about, where on this function. In other words, the derivative, the slope of that tangent line, is a function of x. It's a function of x. So instead of just looking at an individual number and saying, I want to figure out or I want to calculate the slope of the tangent at that point, we also want to be able to find a general function that gives us the slope of the tangent line at any point, depending on x. So what we do then is we look at the derivative as a function. And here is our definition. Okay, so you see what the difference here is from what we had before. You can check the notes from the last our last discussion. Instead of having the limit as h goes to 0, in other words, the distance between these 2 points of x, or I'm sorry, h plus a being some specific point, we're now talking about x, any point x. So this is now a function of x. Okay, and what this does, to look at Desmos again, it tells us what the derivative is at any point here. And you can, once you find that derivative, you can plug in your x and you can find what that derivative is at any point at all. Okay, so we're going to find a general derivative, not a derivative at a specific point that gives us a number. And that's what we get. When we took that derivative at a point, we would get a number. Here, when we take a derivative of a function, we're going to get a function. Not just a number, but a function that we plug x into, and we can find out the value at any point x. Okay, so let's give this a try, and let's do an example of this. So let's say we have the function f of x equals, I'm going to do a relatively simple one, 2x squared. And I want to find the derivative. Not the derivative at a specific point. So this of course looks something, it's some kind of parabola. Okay. We're not looking for the derivative or the slope of the tangent line at a particular point. We want a general formula, a function that's going to give us the derivative at any point, and when we plug in x. So let's try this out. I'm going to use this formula. So the derivative of the function f equals the limit as h goes to 0 of f of x plus h minus f of x over h. So I'm going to put in the only thing I have right now is the h. I know my f of x, that's minus 2x squared. I didn't yet figure out what f of x plus h is. We've done this with the number, with the f of a plus h, but let's do this now. So if we have our f of x here, I need to figure out first our f of x plus h. Let me give myself some room here. So our f of x plus h is, wherever there's an x, we plug in x plus h. So we have 2 times x plus h squared. And I'm going to plug that in here. 2 times x plus h squared. So there's our derivative. It involves x's and h's. Now, before we had h's, and the h would approach 0, but we had a specific number in here where we have the x now, and we would end up with a number, the derivative at that point. Here, we're leaving it in terms of x. So let's figure this out. So this equals the limit as h approaches 0 of, let me expand this here, 2 times x squared plus 2xh plus h squared minus 2x squared over h. That's an h in the denominator there. Equals the limit as h approaches 0 of, and I'm going to just distribute here, 2x squared plus 2xh plus h squared minus 2x squared over h. And we have the limit as h goes to 0. Here, the two x's cancel out, 2x squared minus 2x squared. And we just have our 2xh plus h squared over h. And here, I'm going to now factor, as we usually do. And I'm going to factor out the common factor here, which is an h, leaving me with 2x plus h over h. Here we see that these x's cancel out. H over h is just 1. So we have the limit as h goes to 0 of 2x plus h. And at this point, we can just plug in our limit now. Wherever there's an h, I put in a 0. We end up with 2x. So here is our derivative. And if you notice, it's not just a number, it's a function of x. Okay? So our derivative of our function is still in itself a function of x. What do we do with this? Well, this allows us, let me write this again, the derivative of f of x is 2x. This allows us to figure any point, a derivative at any point. Let's say we want to figure out the derivative at 1. We plug in 1 for here. 2 times 1 is 2. So our derivative at when x is 1 is 2, and so on. We can also say the derivative at -3 is 2 times -3, which is -6. And we can plug in anything. That gives us the derivative at any point on the function where in its domain, where the derivative exists. And this can be very helpful, and we're going to use it a lot. And you can use it to find anything we found before, but you can use it also in proofs, and there's a lot of other uses for it. This is extremely important. This is the basic derivative. We call it the derivative, and this is the limit definition. And no matter what we do, and we are going to in future sections find different ways of doing this faster and calculating derivatives faster, but it will always be based on this definition. This definition will always be there. So it's something that you certainly want to be familiar with. All right, so let's talk or get the idea of what these functions look like. Again, I'm going to use my my Desmos. Okay. So here we have a function. Okay, it happens to be a cubic function. It's x squared, or I'm using t's here, but it's the same thing. Negative t cubed plus 3t plus t plus 2. That's our red function here. Okay. And the purple line is, of course, our tangent. So once we have the derivative of this function, we can plug it in and find the derivative or the slope of this tangent line at any point. Well, as we just mentioned, the derivative is itself a function. Okay, so that function in this case looks like this green function. It's a function also, and let's see why. I'm going to back up a little bit. So we'll look again at the slope of the function. Keep in mind the red function is our original function. That's our f function. The green function is the graph of the derivative. So let's look at the slope of the tangent line. When we're up here, when x is around -2, let me get it on -2. What is the slope of this tangent line? Well, without figuring it exactly, the slope of this tangent line is very negative, right? You can see that it's a very negative slope. And so at -2, the value of our of our derivative is very negative. It happens to be way down here at about -9. Okay, so keep in mind, this green function is the derivative. When x is -2, our derivative is approximately -9. It probably is exactly -9. I just can't land on there exactly. Okay. Let's look at the derivative at another point. We move over a little bit here. Okay, like, let's try to get it over here. Like right before this point, the derivative you can see is still negative, but it's not as negative as it was before. So at this point right here, it's still negative. It's somewhere around here. I'm just estimating, right? Again, the green is the derivative, the graph of the derivative. So when x is -1.1, the value here is -6.3. So it's still a negative slope. Okay. But that's what it represents. It represents the slope of the tangent line. Let's move again a little bit. Let's go to this point here. So now it's flat. In other words, it's right at that point here, and the tangent line is horizontal. Okay. The slope of a horizontal line is 0. So the value of this green function, which is the derivative, is 0. What happens as we move to the right a little bit more? Well, the function now, or the derivative of the function, or the slope of the tangent line, is now becoming positive. And you can see the green value here is positive. Okay. How long does it stay positive? Well, let's keep moving. It stays positive. It keeps getting positive, but now it's getting less positive. Okay. When we get right to here, that's the most positive it gets when x is 0, it looks like. It's very positive. Again, the slope of the tangent line is our derivative. That's the highest value. It's positive, the highest positive value. If we keep moving to the right in this example, it's still positive, but now it's going down, right? The slope of the tangent line is still positive right when it's here, right? But it's going down until it hits this point right there, where once again it is horizontal, right at the top of that hill. The slope of the tangent line at that point is 0, and you see the value of this function here is 0. Okay. So the graph of the derivative function, remember that the derivative is a function in itself, that reflects the value of the slope of the tangent line as we move back and forth. Anywhere you look at this, what you can do is just look at that function, that tangent line, and say, well, the slope there is very negative. The value of the function of the derivative is going to be very negative. When the slope of the tangent line is 0, the value of our derivative, the value of our function, the derivative function, is going to be 0. Okay? So you should be able to, in your mind, plot that, generally draw the graph of a derivative by looking at the function. If you didn't have this there, you should be able to draw that. You should be able to draw the graph of the derivative by saying, well, I know over here, when x is to the left there, that value is going to be very negative because the slope of the tangent line is very negative. It's still negative, but it approaches 0, and it hits 0 right about here. And then it keeps going and going through it becomes 0, and then gets more positive and more positive till it gets the maximum positive that we can get, the highest positive number. And then it starts going down. It's still positive, but going down until it hits 0 again. And you should be able to trace your graph that way. Maybe more difficult, a more difficult thing to do is to kind of go the opposite way. And you start with the graph of the derivative, and you graph what the function might look like. And that's a little trickier, but try it on your own. Keep in mind that this represents the slope of the tangent line of the function at any point. So the slope here is negative. It's getting less and less negative until here the slope is 0. Okay. Think of what that means. Give that a try on your own. Work through those until you can go back and forth with these, and then you'll have a very good understanding of the relationship between a function and its derivative. The last thing I'll mention in this section has to do with continuity. And we've talked about continuity already in the last unit. And I just want to say one thing for continuity here. If a function is differentiable, remember we said that differentiable means that we can take that limit. We can find this limit right here. If we get a limit and that gives us a number, if it's differentiable, then the function has to be continuous at that point. If it's differentiable, it is continuous. Okay, so let me just write that. Differentiable implies continuity. So let's see what that, just kind of look at what that means. Well, if something is differentiable, that means at wherever it's differentiable, we should be able to find the slope of a tangent line. We should find that limit. That limit should be valid. The limit should exist, I should say. Okay. If this limit exists, it's differentiable. If it's differentiable, it's got to be continuous. If there was a hole right here, that would be discontinuous, any kind of discontinuity. We wouldn't be able to find, we wouldn't be able to take the derivative at that point. It wouldn't be differentiable at that point. And you can check and see why that is. Keep in mind that it's not the same as the limit of the function as we're approaching that point. Because if you remember, the limit doesn't depend on what's happening at that point. It only depends on what's happening to the left and the right. However, this itself is a function. This function here is different than f of x. We're not just talking about f of x approaching from the left and the right some point. We're approaching saying this function, does this exist? And it doesn't. It approaches, and you can try that out. It approaches two different numbers at points where we have a discontinuity. So the bottom line here is differentiability implies that it has to be continuous. It does not work the other way. Continuity does not imply differentiability. So just because a function is continuous at a point doesn't mean you can find the derivative. And I'll give you an example, a couple of the little examples here. Say we have a function that looks like this. Okay, so it does all this. It's differentiable all these places here. Everything is, we can find, imagine putting finding a tangent line. There would be a tangent line. We can find a derivative. We can find a derivative there. What happens if we have it here? Well, this would be a different story. There's no specific one tangent line. Okay? And we would not be able to find a derivative there. It's not differentiable at that point where we have a sharp turn like that. It would also not be differentiable when we have a hole in the function. We also would not have a derivative at a point like this. Say we have a function that looks like this. Okay. This could be, for example, f of x equals the cubed root of x, something like that. Well, at all of these points are differentiable. Everywhere here you have that you can find the slope of a tangent line. Right here at x would equal 0 in this case, your tangent line would be vertical. If you remember, the slope of a vertical line is not defined. It's not 0. 0 would be when you have a point that is a tangent line that's horizontal. This is undefined. So that would be undefined, and that is continuous, but it's not differentiable. So it's just something to remember. We'll use this idea later about differentiability implying continuity. And that's it. Give these concepts a try. It's very important to actually do it yourself and write down numbers and look at the graphs and try to figure these things out. Connecting your hands and your brain make a big difference with this. So as usual, ask questions and work on and get help when you need it.